Welcome to Math 31. This is a lesson on curve sketching. So we put the whole thing together now, all the graphing things that we've done, the individual components, second derivative analysis, first derivative analysis, etc. like that. Put it together and we get a finished product, a graph. So you'll be surprised at how good you are at drawing previously ungraphable functions. So typical instructions would be sketch the following and indicate the domain, intercepts, asymptotes, symmetries. Symmetries, as has been noted before, is less important than the other ones, but still, we'll do it. Local extrema, points of inflection. So these are really the big components of the whole thing. For most of the graphs, I'm going to assume that we're going to do things in exact values, unless it states otherwise. So just to warm up, take a look at a fairly straightforward fourth degree expression. Now we don't expect anything weird to happen with this, and in fact, even without looking at things like points of inflection, we can get a fairly good graph. But we still have to go into a little bit more detail. Nice place to warm up, though. So the domain as expected for these types of polynomial functions, there is no restriction on the domain. And as far as the intercepts go, so we really just do this checklist of all the points that we'd noticed. So the intercepts, well, I'll do the y-intercept first. It's easy. So set x equal to 0. So we would get f at 0 is equal to 0 to the 4 minus 4 times 0 cubed. So that is equal to 0. So it means our y-intercept is going to be 0, which tells us as well that there will be one x-intercept also that is at 0. So we set y equal to 0 to find out what the other ones are. Now we would expect at most to be 4 x-intercepts. So 0 is equal to x to the 4 minus 4x to the 3. Solve away. Now typically you'd factor out the largest power of x we can, which would be x to the 3, leaving us with x minus 4. So now we would have x to the 3 is equal to 0. So x is equal to 0. Now if you think back to the old days in math, you would say that that was a root with multiplicity of 3. So you could think of it as there being 3 x-intercepts at that point. But that's all. I'm not going to worry about that. We just take the two intercepts of 0 and 4 and work with those. Now, after we get that done, we take a look at consider the asymptotes and see if there's anything that's noteworthy happening with these. So for asymptotes, we would note any vertical asymptotes are none, right? There's no denominators. Horizontal asymptotes, there are none either. If you took the limits, you'd see that there would be that the y values would be increasing or decreasing without bound. In this case, actually increasing. And then symmetries. Let's see what can happen with that. So I'll make a note that there are no asymptotes. And then symmetries, well, for symmetries, in case you have forgotten, you replace x with negative x, and then you see where it takes you. So we'll replace x with negative x, we get negative x to the 4 minus 4 times negative x to the 3. And then negative x to the 4, raise that negative to the 4th exponent, we get x to the 4, and then we get minus 4, so we times negative x3 becomes, the two negatives become this. Now, the rule is that if f at negative x is equal to f at x, that is, if the function is unchanged, it's even. If f at negative x is equal to negative f at x, then the function is odd. So we try to make sense of this whole thing, and it's neither even nor odd. If you took out a factor, well, you wouldn't even want to take a factor of negative 1 out. So I'll say this, f at negative x, it's probably easiest just to tell like this, is not equal to f at x, and f at negative x is not equal to negative f at x. So therefore, neither even nor odd. The other way to look at that would be to say that there are no symmetries. Now, to get the local extrema, I'm going to have to do first derivative analysis on this one. So I will take the first derivative and see what happens with all of that. I'm going to do it right here. It's a little cramped for space, but this one will work nicely. F prime at x is equal to 4x to the 3 minus 12x squared. And then we look for the critical numbers. So the critical numbers are found where f prime at x is equal to 0, or where it doesn't exist. Now, there are no points where this doesn't exist, so this is all we need to worry about. So 0 is equal to 4x to the 3 minus 12x squared. Take out a factor of 4, and then also the x squared, and that leaves us with x minus 3. Set both to 0. 4x squared is equal to 0, so x is equal to 0. X minus 3 is equal to 0, so x is equal to 3. So these are our critical numbers. So when we do our first derivative analysis, we note our factors. Now we have a choice with this x squared. I'm going to write it all together. The 4 isn't necessary, but I'll keep it there anyways. And then the other one is x minus 3, and then f prime at x. So the critical numbers are 0 and 3. So 4x squared, when x is positive or negative, we would expect that factor to always be positive when we square it. X minus 3 will be positive when x is greater than 3, but negative when it's less than 3. So therefore, the first derivative is negative there, and positive there. So it's decreasing, and then it's increasing. So I'm going to bring up a new screen and get a little more space to work at, but we are not getting a minimum at 0. We're getting a minimum at 3. There is no maximum to this function. So therefore, there's a local min at x equal 3. Now we find out what the y-coordinate is, so f at 3, go back into the original, make sure, and plug into that function, so 3 to the 4 minus 4 times 3 cubed. So when you work that one out, 3 to the 4 is 81 minus 4 times 27. So we're going to get an interesting graph for this one. So work this one out. So 81 minus 4 times 27 should give us negative 27. So f at 3 is equal to negative 27. So 3 comma neg 27 should be the minimum value. So we file that information away, and then when we graph it, now unfortunately I've made it a little too easy for you guys, because on the graph we don't actually have to build our own graph with it. Rather, we can just look at what we have. But some of them we will be doing on our own, and we can still do it pretty much step by step. The key is to get all the information, of course. You're never going to be evaluated on your drawing ability. Now, the second derivative analysis, points of inflection. So second derivative analysis. So we take that first derivative, which I'll rewrite this, so I have it in front of me, f prime at x is equal to 4x to the 3 minus 12x squared. Now we take the second derivative. So f double prime at x is equal to 12x squared minus 24x. So we look for the possible points of inflection. These would occur where the second derivative is equal to 0 or doesn't exist. And again, because it's a polynomial function, it will exist everywhere. So 0 is equal to 12. I'll take out a factor of 12x, and that would leave me with x minus 2. So when we set this to 0, 0 is equal to 12x, and then x minus 2 is equal to 0. We get x equals 0, we get x equal 2. And then we go to the graph and we do our second derivative analysis. So the one factor is 12x, the other factor is x minus 2, and then this is our second derivative. And we get 0, and we get 2. X is positive when x is bigger than 0. And negative when it's less than 0. X minus 2 is positive when x is above 2, and then negative when it's below. So the second derivative is positive, it is negative, it is positive. So if it's positive, we would recognize that as being concave up. If it's negative, it's concave down. And then if it's positive again, concave up. So we do have points of inflection at x equals 0 and x equal 2. So we end up with these 2 points of inflection. If it changes concavity, at that point it's a point of inflection. So we need to find out what the y coordinates are. So we go f at 0, and f at 0 is going to be equal to 0, and it would be f at 0 is equal to, right back in the original, 0, 4 minus 4 times 0 cubed. We've been here before, because that happens to be an intercept as well. And then f at 2 is equal to 2 to the 4 minus 4 times 2 cubed. So f at 2 is equal to 16 minus 32. So I guess that's going to take us to negative 16. So therefore it's 2 comma negative 16. We would say point of inflection at 0, or 2 points of inflection at 0, 0, and 2 comma negative 16. Now, this gives us enough information on the graph to draw it. So what I would normally recommend is to start at the beginning. Start with your intercepts. And we don't have any symmetries, so we can't do much to shortcut that. But if you go to your graph, and here we actually do get to look at it, so it's cheating. We have an x-intercept there, and we have an x-intercept there at 4. And then the graph, as we has a minimum value right there at 3, negative 27. So we know that the graph is going to be above that, and that's going to be its low end. We know that the graph is decreasing all the way down to this minimum value. And in fact, it makes sense based on the graph that it's going down all the way to 3, and then it's increasing from 3 onwards. And then we can see that we have a point of inflection. And that's not that hard to draw because we can see the graph is concave. If you're up to the left of that, it's clearly concave up. The graph is, the cup is up, changes into concave down at that point, and it's oops, yeah, okay, we're okay. And then finally, at x equal 2, and this is probably a little harder to tell where that is exactly, it changes back into concave up again, and it remains concave up for the rest of the graph. So you'd want to graph it in the order that you get it. We take those x-intercepts, we mark them off, and then we go on to the max-min, and then finally the points of inflection to get some shape for it. So this one, as I said, was a little bit too easy because it was given to us, but the method is what you'd always do. You're not going to be judged on your graphing ability, rather you'll just be judged on having all the points correct, as long as you don't totally butcher the graph. Now, let's do one more right now, and then we'll take a look at a few more afterwards. So f at x is equal to 1 over x squared minus 1. Feel free to stop me and go through this one if you would like to, and then compare your answers. When you take a look at the domain, be careful with this. The denominator cannot be equal to 0, but in fact, there's no way that that can be equal to 0. So the domain is simply all real numbers. So x squared plus 1 will always cannot equal 0, would imply that x squared is equal to negative 1. So to change that to so there is no restriction. Now the intercepts are interesting. So your y-intercept, if you set x equal to 0, you get y is equal to 1 over 0 squared plus 1. So y is equal to 1. So 0, 1 for your y-intercept. And then your x-intercept, there is none. If you set y equal to 0 and try to solve this, you'll get no place. It cannot be equal to 0. So there's no x-intercept. So interesting. Move on to the asymptotes and try to make some decisions on that. I don't think you're going to see anything too remarkable happening with the asymptotes. There's no vertical asymptote. There's no way that denominator can be equal to 0. Now, as for a horizontal asymptote, well, take the limit as x increases or decreases without bound. Now, you don't even need to do any simplification of this. 1 over x squared plus 1. If x increases without bounds, 1 over that number is going to get closer and closer to 0. And the same thing is true if you go the other direction. As x decreases without bounds, square the number, it's going to keep getting bigger and bigger and bigger, whereas 1 is staying the same. So we end up with y is equal to 0 as a horizontal asymptote. And then move on to the symmetries. If you were to go f at negative x, you would get 1 over negative x squared plus 1. So f at negative x, simplify that, and you get 1 over x squared plus 1. So in fact, f at negative x is equal to the original function. So this is going to be even. Now, I'm not going to write this down, but it means that it is symmetric about or with respect to the y-axis. Now, if we wanted to, we could use that to save a little bit of time. But instead, I'm going to get a little more space to work, and then, actually, I'll take this back, yeah. And then I will do the first derivative analysis. So you might want to take this function and write it in an easier form to differentiate. So how about x squared plus 1 to the negative 1? So therefore, the first derivative is equal to negative x squared plus 1 to the negative 2. So in a form we can work with mathematically, could say that this is negative 1 over x squared plus 1 to the 2. With this, we should be able to, oops, in all the fuss, of course I forgot there's a 2x there. So negative, let's quickly change that before we get ourselves into any trouble. So negative 2x over 1 plus x squared to the 2. Find the critical numbers. Critical numbers occur where f prime at x is equal to 0. So this is going to be 0 is equal to the numerator, negative 2x. So x is equal to 0. That's our first critical number. Now the other ones would be found where f prime at x doesn't exist. So that would be where x squared plus 1 to the 2 is equal to 0. Take the root of both sides. X squared plus 1 is equal to 0. X squared equal to negative 1. So there'll be no critical numbers. You can't find anything. There's no way x squared can be equal to negative 1. So then the critical number we're going to get is going to be 0. So that's interesting. So then your analysis could look something like this. Our first factor of the derivative is negative 2x. The denominator is x squared plus 1 to the 2. And then when we record the signs, be really careful, because if x is positive, then the derivative will be negative, and then it will be positive to the left of 0. And then x squared plus 1 to the 2 is positive everywhere. So it's positive here, it's negative there. So the graph is increasing, the graph is decreasing there. So we do have a local max at x is equal to 0. So I'm going to get some space, and I'll go further with that. So a local max at x is equal to 0. So when we find out what the y-coordinate is, f at 0 is equal to 1 over 0 squared plus 1. So f at 0 is equal to 1 over 1. So 0, comma 1. Now you could put this on the graph right away, and that's, if you wanted to, that's going to be the max value. Now we do the second derivative analysis. The first derivative, as we had it written, f prime at x is equal to negative 2x over 1 plus x squared to the 2. So this would be a little bit more of a problem to differentiate. You'll have to use the, it's recommended that you use the quotient rule with this one. And u is equal to negative 2x. U prime is equal to negative 2. V is equal to 1 plus x squared to the 2. So V prime is equal to 2 times 1 plus x squared multiplied by the derivative of the inner, which is 2x. So V prime is equal to 4x multiplied by 1 plus x squared. So therefore, y prime is equal to u prime, so negative 2 times v, so 1 plus x squared to the 2, minus u times v prime, so that's minus negative 2x times v prime, which is 4x times 1 plus x squared. So what happens, of course, when you're taking the second derivative is that you don't always get a better form to work with, unless it's a polynomial function. So then 1 plus x squared to the 2, and then squared. Now, I'm not going to spend an awful lot of time working through this one, because it is going to, when you simplify it, it's not anything that you've had that you haven't seen before. So I'll go right to this point. The second derivative is equal to, when you do break this one down, you're going to get it's equal to